I hope students, I'm audible to no, I'm not. Okay. So yes, online students, I'm audible, right?
Yes, sir.
Yes,
Yes, sir.
This has to come yes together, even in online. That gives a lot of so radiation heat transfer between black bodies. Okay, so let us go with radiation heat transfer between black bodies. Black bodies. Radiation heat transfer between black holes. It's very simple, nothing great. So you have one black body here at T1 has an area of A1, and then there is another black body here. Okay, there is another black body here. There is another black body here. Okay, and this A1, this is having T2 and E2. A. Now let us have this is only these are all insulated. We will say although radiation insulation can be there still. Okay, let us say it's insulated, opaque, okay, all those things. So it's only this much is heated. So this is A2. Let us have this insulated like this. So this we are not worried, its backside is going, so it's coming from this side only. So that's it. Okay, so now Q dot 1 to 2 is equal to radiation energy leaving entire surface 1, the radiation leaving surface 1 and striking surface 2 minus radiation energy leaving surface 2 and striking surface 1 and striking surface 1. This can be written as equal to A1, or what is the energy leaving it? It is EB1 into A1 into F1 to 2 minus EB2 into A2 F2 to 1. F is the view. Makes sense? So Q12, this can be written as since since A1 F12 is equal to A2 F21, reciprocity theorem, from reciprocity theorem okay, Q12 can be written as equal to A1 F12 into EB1 minus EB2, that is equal to A2 F21 into EB1 minus EB2. What's the last number we have got here till now? The last number we had is, oh, we forgot numbering, is it not 47? This can be 48. Okay, you can write it later on. 48. This can be 49. Summation theorem can be 49. Then this is okay. This is okay. This one can be 50. So now we will go with 51. Okay, 51 not yet come. Okay, Q dot 12 can be written as A1 F12 into sigma, which is the same, right? Sigma we will take out into T1 to the power 4 minus T2 to the power 4, which can be equal to A2 F21 sigma Stephen Boltzmann constant into T1 to the power 4 minus T2. Let this be equation 51. This is the primary way of heat transfer between two surfaces. Is the primary. Make sense? Done. Agoita. Sir, next. Radiation heat transfer between diffuse gray surface. Radiation heat transfer between diffuse gray surface. So it is diffuse. You know what is diffuse, is it not? It will reflect or emit radiation in all the directions equally. That is called diffuse. Okay. So what we have is in general. Okay. So the total energy. Okay. The total energy radiation leaving the surface is called radiosity. Is it not? Okay. The total radiation energy leaving a surface is called radiosity. It's called radiosity. Radiosity represented by J. Correct? Radiosity represented by J. Okay. Now, um, now, what happens here is radiosity is Ji of any I is equal to the radiation emitted by surface I plus radiation reflected by surface I. Correct. Okay. Now this can be equal to epsilon, which is the emissivity, into EBI plus rho I reflectivity into the amount of irradiation. What is coming on this? What is the incident on it? Irradiation, right? So this can be written as this reflectivity, can be written whatever is reflected. If it is an opaque surface, okay, gray surface is the one, okay. So if this is very important, this Ji you write it here and write this as equation number 52. Important. This is general equation, but then EBI you can have whatever the whatever EBI is there, sigma into T power 4, that we can take it there. Okay, and here GI whatever the radiation intensity which is falling on, not intensity, radiation falling on. If the intensity is given, you have to multiply by pi and get that GI. Is it not? Hemispherical, this one, hemispherical radiation. If you have intensity given, then the total comes with a hemisphere around it. Got it? Around the hemispherical one, you have to integrate, right? So you have to do multiply by pi if it's a diffuse radiation. Correct. So these are all the things, okay? Or if it is in all directions, you can. Okay. So now Gi is that. Now if the if the surface I is gray and opaque, gray and opaque, then 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 since gray and opaque, since uh, alpha plus rho plus tau is equal to 1 and tau is equal to 0 implies alpha plus rho is equal to 1. But applying Kirchhoff's law, applying Kirchhoff's law, applying Kirchhoff's law, we can write epsilon I, provided that is at the temperature which is constant. Okay, it's a constant temperature. Okay, so alpha I, epsilon I is equal to alpha, epsilon is equal to alpha, right? Epsilon is equal to alpha. Therefore we can write Ji is equal to epsilon I into EBI plus, okay, because of this we can write rho is equal to epsilon alpha minus I, alpha minus or 1 minus alpha, 1 minus alpha, which is equal to 1 minus epsilon. Correct? So we can write here 1 minus epsilon of I, this you write as I of that surface, epsilon I into Gi. Very, very important. Very, very. So you see where the Kirchhoff's law is applied, is it not? Okay. So it's very, very important. 53. Make sense? If the surface is black body, then you get epsilon I is equal to 0. Sorry, epsilon I is equal to 1. So 1 minus 1 becomes 0, you get black body radiation. Makes sense? So between these 2 points, how the things goes? It goes like this, okay? So let us understand this. Write down easy. Don't worry about anything else. Just write it. ಅದಕ್ಕೂ ಹೇಳಿ. ಮಾಡುವ ನೆಕ್ಸ್ಟ್ ಸರಿ. ಈಗ going next, students, okay? So net radiation heat transfer. Now here what is happening from the surface, if you see, this is radiosity, okay? This is radiosity, okay? So now if I say qi, heat transfer, okay, the net rate of heat transfer, the net rate of heat transfer, rate of heat transfer from a surface I, from a surface I of surface area AI is denoted by qi, what is going around the surface, from the surface, what is the heat transfer from the surface. Qi is equal to radiation leaving the surface, radiation leaving entire surface I minus radiation incident on the entire surface I. Correct. What is the radiation leaving the surface? It is AI into Ji, radiosity. That is the amount of radiation which is leaving, which has both emission plus reflection. Right? Agreed? J is what? J is emission plus reflection. So that J which is leaving minus what is coming out, coming on, that is equal to minus AI into GI. What is falling on it? Irradiation. What is falling on it? That's how you get it. Correct. So now this can be equal to, I can write AI into, if I write JI, okay. Now Ji I have to write it nicely. So now here observe. Now here, so this is how it is. Now from equation 53, let us solve for Gi. Okay, from equation 53, we can write we can write okay, uh, we can write we can write Ji or Gi is equal to Gi is equal to Ji minus epsilon into epsilon I into EBI divided by 1 minus epsilon I. Agreed? Just observe whether we can write it from 53. Just see 53 equation. We'll go slow here. No urgency. This you write as 54. Just see fast. Correct. ಬರ್ತದಾ 53 ಇಂದ ಇದು ಬರ್ತದಾ So once you get that, we get substituting in equation 54, we obtain qi dot, what is leaving, is equal to, we can write ai into ji minus epsilon I ebi divided by 1 minus epsilon I, which can be written as equal to, I'll take this side, so you will get ai into ji into 1 minus epsilon I minus ji plus epsilon I ebi divided by 1 minus epsilon I. Correct. So from this you see ji here plus ji here minus gets cancelled. There is ji multiplied by epsilon I, which is minus. Here you have epsilon I ebi. That you have to keep in mind. Next, I'll write it. Okay. Very, very important. This is, student. This is the crux of radiation heat transfer. Goida? Then, okay. Next. Now what happens? We will write this as qi dot is equal to, I can write ai epsilon I divided by 1 minus epsilon I into ebi minus ji. ebi minus ji, which will give us, okay, now this one I can write in this also, this you write as equation number 55. Very important. 54 is or 55. Very important equation. This is very important. So now this can also be written. See, sometimes we use radiation, what you say, resistance concept. So the heat transfer Q, which is leaving this, actually has a resistance, and then it goes to Ji. That is what we see. We see it starts from EI, which depends on the black body radiation, is it not? EBI is the black body radiation. So we can consider this as EBI to Ji, with this being the resistance. Now, what is the resistance here? Resistance can be written as Qi dot is equal to EBI minus Ji divided by resistance of radiative heat transfer resistance. Very important, this one also. So this is 56. All are important. Where Ri is equal to 1 minus epsilon I, very important, 1 minus epsilon I divided by AI epsilon I. This is the heat transfer, radiation heat transfer resistance. Based on this, everything is calculated. Clear? So what is happening? This, we say everything is black body, but gray body absorbs in between something. Gray body means it's not emitting everything, is it not? That means whatever it is emitting, it's absorbing. That's what we think. And because it's absorbing, it has some resistance. Getting the point? If it was a black body, it would emit everything. But if it's a gray body, something it will absorb. It will not emit everything, right? As high energy as a black body. So what that difference is that we say it absorbs those things. We are assuming that black body emits everything, but not every body emits it. So gray body emits equally like a black body, but not to that extent in that wavelength. So what do we say? That much energy it's absorbing. So when it's absorbing that energy, it should have resistance. That resistance is represented here, where absorption is equal to emissivity. Why? It is at the same temperature. Observe here, this is very, very important. How did we say that alpha is equal to epsilon? Because what it is absorbing is its own radiation, which is radiation coming out of it, emitted radiation. So that's how we can aim at this. Correct. Sure, right, Mr. Ri is called surface resistance to radiation. Ri is surface resistance radiation. Five minutes, I have to call one person. Okay. So I will give something and then I'll go. Okay. I do it now. Just review that. Okay. Done. Okay. Now here, if there is a heat transfer between two surfaces, I have one surface gray body here. This is gray surface J or gray surface I, which is this, and then we have gray surface J. Surface J. What I'll have, I will have, observe, we will have, okay, Qij. We have two J's, okay. So here we have a J, here we have a J. Understand first, okay. We have a J here, we have a J here. This is EBI. This would be JI. This would be JJ, and this would be EBJ. In between there will be a resistance. What would this be resistance? This would depend on the view factor. How it will be? We know that Q is equal to A into Fij into sigma into T1 to the power 4, Ti to the power 4 minus Tj to the power 4. Correct? So what is R here? This can also be written as Q is equal to, Q can be written as equal to, between students, okay, 1 minus the sigma is there everywhere, don't worry. So yeah, so this I'll write this like this, not like this, okay. I'll write this as EBI minus EBJ. Instead of that, this is similar to having between J's, between this point and this point. What it will be, here in general we can write EBI minus EBJ divided by R, Rij, which gives us where Rij is equal to 1 by A into Fij. Make sense? So we can have EBI to EBJ, and in between you can have resistance R, which is equal to 1 by A Fij. Make sense? Similar thing here, I can have this as Ri, which is equal to here Ri. I can have Rj, which is surface resistance, and here I can have Rij, which is equal to 1 by A into Fij. That is the heat transfer which is happening. So if I want to write Qij, Qij should be equal to Ai into Fij into Ji minus Jj. Got it? Now Qij is equal to Ji minus Jj divided by Rij, which is equal to Rij is equal to 1 by Ai Fij. Make sense? So like that you write this one, students. This one would be, yeah, all the equations we have: 57, 58, 59, 60. 58, 59, 60. I'll tell you more in a minute. Okay, we'll go more deep into it. Chalo, let us go. I'm very sorry, students. There is yesterday's class I missed. Yesterday's meeting I missed. So some things has to be done. Okay. Don't worry, students. Okay. Chalo. Next. Done. Fine. Okay. So now here in this case, this resistance concept is very very important and very very good. Okay. In the sense that, for example, if I have more than one body, for example, if I have more than one body, for example, here, if I have this surface I, say I'll say this surface I, this is surface I will call this as EBI. Then we will have surface resistance, and then we may have, say, JI. This is the surface resistance RI. Now from here, it may go to various places. The heat which is coming out of this QI can go to various others, see, other surfaces. It's possible, is it not? So it may go to surface, say, 1. So what you have here, you will have from this surface resistance, say, surface 1. So this will have point J1. And then here you will have RI1. Here you will have surface resistance of this ring here. This is J2 surface 2. Now radiation problem is converted to electrical networks problem. And actually network problem. That's why network analysis is very important. So I feel sometimes that network analysis has to be taught in the first year for all the engineers. Computer science, mechanical, electrical, electronics, everybody. Electrical, electronics, anyhow they have it. But mechanical and civil, they have to teach network analysis. Important. Kirchhoff's law, Kirchhoff's voltage law, Kirchhoff's what to say, current law. All those things are very important. Okay. Same thing we are applying. Okay. Surface 3. So here we have this here like this. So wires can bend. Okay. Don't wires can bend. So here this is RI2. RI2. Write it down, student. Don't. This is RI3. Make sense? This is J3. Oh, sorry, sorry. This is not J3. This is J3. This is R1, this is R2, this is R3, and then we can have any number. Make sense? ಹಾಗೆ ಅಲ್ಲಿಂದ ಇನ್ನೊಂದಕ್ಕೆ ಎಲ್ಲದಕ್ಕೆ. So it's a big networks it will have. Okay, so resistance networks, wire le papa, kind of things. You understand, when we go to Mumbai or Chennai railway stations, there'll be one person will be standing like this with all the headphones here, all the connections. In Chennai, you get 30 rupees headphone, Here it becomes 50 rupees. And sometimes you get lucky, you get good headphones there. Not always. Some headphones will throw within 1 week. Okay. Some within 2 days, one will hear, one will not hear. That happens. Because there's no guarantee, you see. It does not pass quality control. It becomes good by chance. Then you have to see the probability of it being good. You have to take a sample space. You have to see out of this 10 how many became good. Then you put a normal distribution and see what is the chances, and see what is the what is the cost of the boat earphone. So if this probability becomes more 10, you select, and in that one comes better, then better you take 10 and select which is better. Or else if it goes more, if you have to take 20 or 30, you can get a boat or a Samsung earphone. Or Panasonic, any company. Yes, please. Here the concepts, more concepts through problems I will tell you. Okay, so in 10-15 minutes we'll go towards problems. Concepts through problems. This is the only thing. I think I can complete. Done. Yes, please. Done. Sure. Now let us take radiation heat transfer in two surface enclosure. Okay. The radiation heat transfer. Same thing we are continuing. So radiation heat transfer in two surface. Two surface. Yes, tell me, students. Any doubts here? Where was the sound? Yeah, everything is fine. So two surface enclosure. Go to see that. Okay. So what happens? Two surface enclosure means enclosure made out of two surfaces. It is not two surface enclosures. So it's connected between two surface and enclosure. It's not two surface enclosures. It is two surface enclosure. That means you make the enclosure with the two surfaces. So you have two surfaces, surface 1 and surface 2. So surface 1 and surface 2. So this is surface 1 and this is surface 2. So here you have surface 1 and you have surface 2. Okay. So surface 1 is inside, I'm sorry, it's not outside, it's inside. Surface 1, surface 2, inside. So enclosure made out of it. Okay. In between is the vacuum, otherwise we have to add that is another surface. That much depth we will not go, we will stay what is required for gate. There is a possibility that that will also be a surface. Gas is also considered as surface because it absorbs. Gas can absorb energy, is it not? Getting the idea? Okay. So this one, if the surface is like this, write it neatly, students. There is a joint here, so there's a joint here. Okay. Now, here when we take this like this, what happens here is you take this, you go with heat transfer, which is going as Q dot 1, which goes from EBI to J1 or EB1 to J1, EB1 to J1, and then you go to the second one and you say that is J2, and what goes through this is Q12, Q12, and what goes from here to this to EB2 is Q2 dot. Fine. Now here radiation R1, radiation surface resistance is 1 minus epsilon 1 divided by A1 epsilon 1. This would be the in between R12 would be equal to 1 by A1 F12. R2 would be equal to 1 minus epsilon 2 divided by A2 epsilon 2. Make sense? A2 epsilon 2. Good enough? Okay. Now Q12, since the resistances are in series, Q1 dot is equal to Q12 dot is equal to Q2 dot, right? Or minus Q2 dot, minus Q2 dot, because it is whatever is going into it. Okay, so that way we can write. So what is Q12? Q12 can be written as all the resistances combined together, 1 EB 1 minus EB2 divided by R1 plus R12 plus R2, which is equal to Q1 dot, which is equal to minus Q2. It is receiving it, is it not? So receiving is Q2. So now what is R1 plus R2? So R is equal to R1 plus R2 plus R3, which can be written as 1 minus epsilon 1 A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 divided by A2 epsilon 2. So till now what is the equation we have? 60. Okay. So 60 is over. So now what we can write is Q dot 1 to 2 is equal to sigma into T1 power 4 minus T2 power 4 divided by 1 minus epsilon 1 divided by A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 divided by A2 epsilon 2. Very, 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 very important. This is 61. Very, 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 very important. This is the crux. Almost 40% comes on this one and related to this, whatever we have done today. So let us see specific cases one by one. Although it looks difficult now, students, it's easy, very easy. Okay, you will see while we do problems. Done. Because it's receiving. What is coming to you is minus. Thermodynamics. It's what is receiving. Ah, it's about the direction also. You see, Q1 is going in this direction. In with respect to this, it is going in. It's negative. Let's no, don't worry about it. Okay. When we do problems, you'll understand. It's all intuitive. Okay. So now let us see some specific issues. Some specific heat transfer arrangements. Radiation heat transfer arrangements. Radiation heat transfer arrangements. Let us see one by one. First one would be small object in large cavity. A lot of questions on this which has come, students. Small object in large cavity. Small object in large cavity. If you have a large cavity, write it along with me, student. Nothing great here. And you have a small object which is at A1, T1, epsilon 1. And this is a large cavity. Very, 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 very large cavity. Okay. Then this will have A2, T2, epsilon 1. Then here in this case, A1 by A2 is almost equal to 0 and F1 to 2 is equal to 1. Therefore, Q12 would be equal to A1 sigma epsilon 1 T1 power 4 minus T2 power 4. That's it. You understand why? A2 is very small. A2 is almost 0. Okay, sorry. A1 is almost 0. A2 is very big. So what will happen? You observe that. What will happen there? See here, what we can do here is if A1 is equal to A2 and yeah, epsilon 1 here. Okay. So epsilon 2 goes off. Just see that here. In this case, you have, see, since, see, what did we have? We had R is equal to 1 minus epsilon 1 divided, this is derivation for this. This is important. Write this as next one. 61 is over 62. So you will have A1 epsilon 1 plus 1 by A1 F12. Okay. F12, where is F12? F12 is 1, right? So 1 goes off. Plus 1 minus epsilon 2 divided by A2 into epsilon 2, right? So what this will become? This will become R is equal to 1 by A1 epsilon 1 minus 1 by A1 plus 1 by A1. This is almost equal to 0. Since A2 tends to, A2 is much greater than A1. So you can reject this, almost 0, neglect. Make sense? So this will be the case, this cancels. And what you get? 1 by A1 epsilon 1 is the R. That's why you get this. In the same equation, last equation you apply. Understand? Take some time on this. Since. Clear? Yes or no? Bharat, clear in what? ಸರಿ ಅಲ್ಲ A2 ದೊಡ್ಡದು A1 ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ so 1 by A1 epsilon 1 ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ 1 by A2 epsilon 2 is very less. Sorry, 1 by A2 epsilon 2 is very less because A2 is very, very big. So that can be taken almost as 0. See, in R here, this is the R which we have. In R, this is very small. Then you divide 1 by A1 epsilon 1. Epsilon 1 by A1 epsilon 1, epsilon 1 cancels. So you have 1 by A1. F12 is almost equal to 1. F12 is almost equal to 1. F12 is 1. Right? So this becomes 1 here. So A1 and A1 is there. That cancels. And what you remaining? 1 by A1 epsilon 1. So Q is equal to delta T by R or delta E by R. What is that? E sigma into T1 minus T2 power 4. That is there over here. Sigma into T1 minus T2. R has 1 by epsilon 1. 1 by A1 epsilon 1. That goes up. Clear? Right. Very, 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 very important. This is what comes in exam. Most of the questions that comes is on this one. This topic. Tomorrow also we'll have class. Okay. Tomorrow morning also we'll have radiation plus one more. Just being shameless. Afternoon also, evening also we'll have one class. Tomorrow morning one more class. Okay. So somehow I want to be fast, but it does not happen. I know others will complete within so many days. They will take 6 hours. They'll complete radiation. Somehow I cannot. I took around 18 hours. Is it not? Took more. When did we start? ಜಾಸ್ತಿ ತಗೊಂಡಿದ್ದೇವೆ, 10 ಗಂಟೆದು ತಗೊಂಡಿದ್ದೇವೆ ಅಲ್ವಾ. ಫ್ರೈಡೇ ಶುರು ಮಾಡಿದ್ವಾ ನಾವು, ಥರ್ಸ್ಡೇಯಾ? ಸೆಕೆಂಡ್, ಓಕೆ, ಆಗಿದ್ರೆ ಪರವಾಗಿಲ್ಲ. ಸೆಕೆಂಡಿಗೆ ಶುರು ಮಾಡಿದ್ರಿ, ಹೌದು, ಫ್ರೈಡೇ ಶುರು ಮಾಡಿದ್ವಿ ನಾವು. ಫ್ರೈಡೇ ಶುರು ಮಾಡಿ ಆ ದಿನ 2 ತಗೊಂಡ್ವಿ, ಸ್ಯಾಟರ್ಡೇ ಸಂಡೇ ಒಂದು 2 ಗಂಟೆ ತಗೊಂಡ್ವಿ, ಸ್ಯಾಟರ್ಡೇ ತಗೊಳ್ಳಿಲ್ಲ ಆಯ್ತಾ. ಸಂಡೇ 2 ಗಂಟೆ, ಈ ದಿನ 3 ಗಂಟೆ, 2 ಗಂಟೆ ಇಲ್ಲಿ. ಮಂಡೇ 4 ಗಂಟೆ. ಸೊ ಯಾ, ಅರೌಂಡ್ 10 hours ಆಯ್ತು. Yes, that's fine. 10 to 12 hours is required. Okay. So heat transfer took more than 60 hours. We have taken well students. Okay, that's one thing which you have to. And so don't blame me that I have taken too much of time, but it has helped you. Okay, that has to be understood. Okay, sir. November 30th ಒಳಗೆ ಕಂಪ್ಲೀಟ್ ಆಗಲಿಲ್ಲ ಅಂತ ಬ್ಲೇಮ್ ಮಾಡಬೇಡಿ, ನಿಮಗೆ ಒಳ್ಳೇದಾಗಿದೆ ಆಯ್ತಾ. ಸರಿ, ಈಗ ನನಗೆ ಐ ಆಮ್ ಗೆಟಿಂಗ್ ಪ್ರೆಷರ್ ದಟ್ ಬಿಕಾಸ್ ಸಿವಿಲ್ ಹ್ಯಾಸ್ ಟು ಕಂಪ್ಲೀಟ್ ಫಾಸ್ಟ್. ಓಕೆ, anyhow chalo, because this I can do anything, civil I cannot do. What to do? Okay, so there's 2 options, whether give to Velmurugan only or get other faculty. If I get other faculty, what is the headache we have to see? Okay, so Velmurugan is time tested. Okay, chalo, done. Next, now infinitely parallel plates. Yes please. ಲಾಸ್ಟ್ ಈಕ್ವೇಷನ್ ಹೇಗೆ ಬಂತು ಅಂತಲಾ, F12 ಎಷ್ಟು 1 ಡಿವೈಡ್ ಬೈ A1 ಎಪ್ಸಿಲಾನ್ 1 ಇಲ್ಲಿ ಬರುತ್ತೆ. ಎಪ್ಸಿಲಾನ್ 1 ಡಿವೈಡೆಡ್ ಬೈ A1 ಎಪ್ಸಿಲಾನ್ 1, ಎಪ್ಸಿಲಾನ್ 1 ಕ್ಯಾನ್ಸಲ್ ಆಯ್ತು, ಉಳಿದದ್ದೇನು 1 ಬೈ A1. ಸರಿಯಾ? ಕ್ಲಿಯರ್? ಸ್ಲೋ ಹೋಗಿ, ಏನು ಪರವಾಗಿಲ್ಲ, ನಮಗೆ ಗೇಟ್ ಅಲ್ಲಿ ರೈಟ್ ಆನ್ಸರ್ ಸಿಗೋದು ಇಂಪಾರ್ಟೆಂಟ್. ಆ ದಿನ ನಮಗೆ ಹೇಗೆ ಸಿಗುತ್ತೆ ಅದರ ಮೇಲೆ ಎಲ್ಲ ಡಿಪೆಂಡ್ ಆಗಿದೆ ಅಲ್ವಾ. 4th of February ಟಾರ್ಗೆಟ್ ಇದೆ, ಈಗಲೇ ಚಂದ ಮಾಡಿ ಓದಿ ಸಾಕು, ಟೈಮ್ ಸಾಕು, ಏನು ಪರವಾಗಿಲ್ಲ, ಡೋಂಟ್ ವರಿ, ಪ್ಯಾನಿಕ್ ಮಾಡಬೇಡಿ, ಆದರೆ ನಿದ್ದೆ ಮಾಡಬೇಡಿ ಅಷ್ಟೇ. ನಿದ್ದೆ ಮಾಡಿ ರಾತ್ರಿ ಮಾತ್ರ 7 ಗಂಟೆ 8 ಗಂಟೆ ಮಾಡಿ, ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಮಾಡಬೇಡಿ. 10-12 ಗಂಟೆ ಎಲ್ಲ ಮಲಗಕ್ಕೆ ಹೋಗ್ಬೇಕು. ಹಾಗೆ ಮಲಗಿದ್ರು ಬಾಕಿ ಟೈಮ್ ತುಂಬಾ ಯುಟಿಲೈಸ್ ಮಾಡಿ, ನಿಮ್ಮ ಮೈಂಡ್ ಫಾಸ್ಟ್ ಓಡಬೇಕು, ಆ ಥರ ಮಾಡಿ ಆಯ್ತಾ. ಅದೇ ರಾತ್ರಿ 9 ಗಂಟೆಯಿಂದ ಬೆಳಿಗ್ಗೆ 7 ಗಂಟೆ ತನಕ ಮಲಗ್ಬೋದಲ್ವ. 7 ಗಂಟೆಗೆ ಎದ್ದು ಬಿಟ್ಟು ಕ್ಲಾಸಲ್ಲಿ ಇರ್ಬೇಕು, ಹೀಗೆ ಮಾಡಿ ಆಯ್ತಾ. ಬ್ರಷ್ ಮಾಡ್ತಾ ಮಾಡ್ತಾ ಕ್ಲಾಸ್ಗೆ ಇರ್ಬೇಕು. ಹಾಗಾದ್ರೆ ಇಲ್ಲ 8ವರೆಗೆ ಮಲಗಿ, ಬೆಳಿಗ್ಗೆ 6ವರೆಗೆ ಹೇಳಿ, 10 ಗಂಟೆ ಆಯ್ತಾ ಅಲ್ಲಿಗೆ, 8ವರೆಯಿಂದ ಬೆಳಿಗ್ಗೆ 6ವರೆಗೆ. ಸರಿ ಆಯ್ತಾ, ನೆಕ್ಸ್ಟ್ ಆಯ್ತಲ್ಲ. ಸರಿ, ಈಗ ಇನ್ಫೈನೈಟ್ ಲಾರ್ಜ್ ಪ್ಯಾರಲಲ್ ಪ್ಲೇಟ್ಸ್. ನಾನು ಹಾಗೆ ಇದು ಮಾಡ್ತಾ ಇದ್ದೇನೆ ಮಕ್ಕಳೇ, ನಿಮ್ಮ ಹಾಗೆ ಆಯ್ತಾ. ಐ ಆಮ್ ಆಲ್ಸೋ ಸ್ಟ್ರಗ್ಲಿಂಗ್, डोंट वरी, वी विल डू इट, हम होंगे कामयाब इस बार, इसी बार. Now infinitely parallel plates, big plate, very big, very big plate. So these 2 plates will have an area A1, T1 and epsilon. This will have A2, T2, epsilon. ಸರಿ, ಇನ್ಫೈನೈಟ್ ಪ್ಲೇಟ್ ಸರಿ, ಏರಿಯಾ ಎಂತ ಮಾತಾಡ್ತಾ ಇದ್ದೀರಾ ಅಂತ ಕೇಳ್ತೀವಿ. ಇನ್ಫೈನೈಟ್ ಪ್ಲೇಟ್ಗೆ ಇನ್ಫೈನೈಟ್ ಏರಿಯಾ ಅಲ್ವಾ ಸರ್ ಅಂತ ಕೇಳ್ತೀವಿ. ಏನಾಗುತ್ತೆ ಅಂತಂದ್ರೆ ಪರ್ ಯೂನಿಟ್ ಲೆಂತ್ ಎಷ್ಟು ಏರಿಯಾ ಇದೆ ಅಂತ ನೋಡೋದು. You have to see in terms of per unit. Okay, so So that's, so we will say, but anyhow we will say A1 is equal to A2 is equal to A, F12 is equal to 1. This is seeing that totally, it does not have anything to see. It's very big, it is only seeing that. It does not have anything else to see. Okay, that's a problem. Okay, so this Q12 dot is equal to A, area is same, area comes out. Okay, then since area comes out of it, what happens is, and F12 is 1, so you get this as A, area, into sigma into T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 plus 1 ಬರುತ್ತೋ ಇಲ್ಲ ಅಂತ ನೋಡಿ. This is equation number 62 ಅಲ್ಲ 63 ಯಾ 63 ಎಲ್ಲಿಂದ ಬಂದಿದ್ದು 60 ಇಂದ 60 everything starts from 61 61 61 ಇಂದಲೇ ಬರುತ್ತೆ. ಈ ಎರಡು ಅಪ್ಲೈ ಮಾಡಿ ಇಲ್ಲಿ ಬರುತ್ತೆ. ಬಿಸ್ಲೇರಿ ಆರ್ಡರ್ ಮಾಡಬೇಕು ನೆಕ್ಸ್ಟ್. ಸರಿಯಾ, ನೆಕ್ಸ್ಟ್ ಹೇಗೆ ಬಂತು ಅಂತ ಗೊತ್ತಾಯ್ತಲ್ಲ. ಸರಿ, ನೆಕ್ಸ್ಟ್ infinitely long cylinder, infinitely long concentric cylinders. There is one BBC thing which is coming, which is making fun of everybody. That is called, this is called, what the name? Philomena something. It's okay. I was seeing shots. I was very happy with that. So it's Kunk, I suppose. Philomena Kunk. Yeah. Anyhow, sure. Yeah, Philomena Kunk. She makes a lot of comedies. I like that comedy with a very serious face. Correct. Correct. Minus, not plus. Yes or no? Because minus comes over your 1 by minus 1 comes. Observe that. I'll do that again. Okay. So this infinitely long cylinders can wait. Okay. So what we'll have here, you will have 1 by A1 epsilon 1 minus 1 by A1, then plus 1 by A1 A1 F12 is 1 only, right? Then plus 1 by A2 epsilon 2, correct? And then this is R, then minus 1 by A2, A2 goes out, right? A goes out, this comes, this cancels. So this A2, what is there, which is equal to A. So let us have this A is here. So A goes there and you get minus 1, not plus 1. Makes sense? Good. Okay, next let us go with infinitely long cylinders. Okay, if I go with infinitely long cylinders, I'll write it in the next slide. Okay, done. So it's very important minus. So everything when we go from the basics, you can catch the mistakes. ಸರಿಯಾ ಪ್ಲಸ್ ಹಾಕಬೇಡಿ ಮೈನಸ್ ಹಾಕಿ. ನೆಕ್ಸ್ಟ್ ಈಗ ಇನ್ಫೈನೈಟ್ಲಿ ಲಾಂಗ್ ಸಿಲಿಂಡರ್ಸ್ ಹೇಗಾಗುತ್ತೆ? ಲಾಂಗ್ ಇನ್ಫೈನೈಟ್ಲಿ ಲಾಂಗ್ concentric cylinders. If I have infinitely long concentric cylinder, the cylinder inside the other one, ಇದೆ ಈ ಸಿಲಿಂಡರ್, ಇಲ್ಲಿದೆ ಈ ಸಿಲಿಂಡರ್, ಈ ಸಿಲಿಂಡರ್ ಆ ಸಿಲಿಂಡರ್ ಒಳಗಡೆ ಇದೆ ಅಷ್ಟೇ. infinitely long, infinitely long. Tap, 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 tap. This one is R1. This one is R1 and this one is R2. So yeah, ಈಗ A1 by A2 is equal to R1 by R2 and F12 is equal to 1. So what is R? R is generally written as 1 minus epsilon 1 into epsilon 1 A1, right, plus 1 by A1 F12 plus 1 minus epsilon 2 into epsilon 2 into A2, correct? Now let us take A1 outside here. Okay, let us say 1 by A1. If I take 1 by A1 outside, what goes inside? 1 minus epsilon 1 by epsilon 1 plus 1 by F12 plus here A1 goes, is it not? A1 comes out. So A1 we have to add. So we will have A1 by A2 into 1 minus epsilon 2 by epsilon 2. Correct. If you do it much better, you will get 1 by A1 into 1 by epsilon 1 minus 1 plus 1, putting this, applying this over here. Okay, applying these two. Okay, and here you will get it as, observe, here you will get it as plus 1 minus 1 cancels, don't worry, plus here A1 by A2 is R1 by R2 into 1 minus epsilon 2 divided by epsilon 2, no epsilon 1s. So this I can write it as R, I can write it as 1 by A1 into 1 by epsilon 1 plus R1 by R2 into 1 minus epsilon 2 divided by epsilon 2. ಒಂದನ್ನು ನೆನಪಲ್ಲಿಟ್ಟರೆ ಆಯ್ತು, ಇದನ್ನು ನೆನಪಲ್ಲಿಟ್ಟರೆ ಆಯ್ತು, ಬಾಕಿ ಎಲ್ಲ ಬರುತ್ತೆ. Now this one, so we can write Q12 is equal to A1 sigma T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 minus epsilon 2 by epsilon 2 into R1 by R2. Slobana? We have one book by Professor Balaji, which is staying here for a long time. I did not refer to this book now, but it's very important. If you go further, you can refer to this book, Radiation Heat Transfer by C. Balaji, Chakravarti Balaji. He's one of the fantastic teachers in IIT Madras. Okay, very highly respected. for being student friendly as well as not reducing the academic rigor. There are professors who reduce the academic rigor and become student friendly. This person is so efficient that he gets academic rigor along with student friendliness. Obviously, he takes only the toppers, but still, toppers are not that great, is it not? Not always great. Just because they have taken marks doesn't mean they are good. Okay? That we realize it a lot of times. See, 1919 Nobel Prize address by Max Planck on the origin and development of quantum theory. He has quoted this. I felt this is fantastic quote to do from this book. Okay, the quote is like this: "But even if the radiation formula should prove to be absolutely accurate, it would, after all, be only an interpolation formula found by happy guesswork, and would thus leave one rather unsatisfied." Okay. I was therefore, from the day of its origin, occupied with the task of giving it a real physical meaning. It means even if it is there, it was a guesswork, basically. See, Max Planck, H, and all those things. I don't know. I have to go to depth of quantum mechanics and understand how does the radiation formulas come. How do we get this black body radiation? What is the way we have to get it? I don't know. Maybe now physical understanding is there, but I don't know it. So maybe further when we go to the depth of it, we will understand. But keep in mind, we know only the formulas now. We don't know the physical meaning, why that lambda comes, how that Max Planck came with the Planck's law. Maybe it is known by the scientific community today, but we are ignorant. That we have to understand. So, what is knowledge? Knowledge is knowing what we don't know, what we know. So I'm very clear. You can solve the radiation heat transfer problems. What you don't understand, that has to be that has to be understood. That we don't understand the mechanics properly. We have a superficial understanding over the surface. Okay? That will propel us to do something great. We say that we know a lot of things, then what happens? We are stuck there. The moment we say, I know it well, and compare it with the lower people who don't know, we can become great at any point of time. You have passed PUC, you have passed 10th standard, you are better than 50% of the people. Or a lot of people don't pass 10th, but now they do 80%. Okay, you are 80%, best 80%. People who have 10th standard passed. If you take the globe, then you are top 50%. The people who have passed PUC in science, they'll be only 10% of the total population. Fantastic. You have come out of engineering college, 1%. You're 1% of the total population. Oh, fantastic, man. 1% intelligent people. Okay? So, like that, you go. And the people who come to IIT or come to the level of the what you say, institutions that are to the level of IITs, very less, 0.00001%. That you are there. That way you get comparisons. Okay, but that is not the way you have to compare because you will not get the benefits out of it. Okay, done. Concentric space. I am talking to you as if you are in IIT only because I know you will be. Okay, all of you. Okay, in some or the other part of the life. Okay, or in the equivalent institutions. Okay, now concentric space. Concentric space. Now you have R1 and then another sphere. I cannot write any other way. It's concentric, so center is the same. This is R2. Fine. So this R1 and R2. Now here A1 by A2 is equal to R1 square by R2 square. And F12 is always equal to 1. But not F21. Understand that. F12 is there, F21 is not. F1 to 2 is 1, F2 to 1 is not 1. So now with this, we get Q12 dot is equal to A1 sigma into T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 minus epsilon 2 divided by epsilon 2 into R1 by R2 the whole square. Very, very, very important. Last concept is radiation shields. Okay. There's some concept I will do to formulas, not concepts, same concepts, but while we do problems, you will understand much more to the deep. Okay. Then now, oh, sorry, the queen will be. Now there is no queen now. There is king in England, not here. He is not my king, not my queen. Okay. So done. Aita. Done. Oh, what? So next, radiation shield. 5 minutes I will continue. I'll go more than I think radiation shield. So last one, radiation shields. Radiation shields. Now, radiation shields are used to save you from radiation. Where are radiation shields used? They are used in nuclear power plants, wherever we have high heat content, like furnaces, cupola, near that, because it's 1500 so many degrees centigrade. So, one thing to save the energy, another side is to save the people. Okay, so this is required. So somewhere you have, say for example, high temperature which is there here on a particular wall. Say this is a wall of a furnace. Okay, whichever is at a high temperature, not the first wall, the first wall where it is exposed to that heat. Okay, so let us say it can be, this is wall 1 where it is having T1 and it is having a epsilon 1. Okay, now this has to be shielded. Now, how do you shield it is important. You will put a radiation shield which will have two surfaces. It will have two surfaces to save another person here. Correct? This is the radiation shield. This is the shield. Shield to save this T1 heat, what is coming there, to the person T2 here, which has an epsilon 2. Now, the shield has two things. So, whatever the heat which is coming out of here, Q12, Okay, will be the same one here also. Okay, so here this would be, I will write this is T3 epsilon 3 comma 1, means epsilon is for the surface, not for the whole one. It's a surface characteristic. How is that surface characteristic? How is epsilon surface characteristics, not the material characteristic? Is the question you will ask me. I will answer it in a moment. Okay. Now this I will say T4, and this is epsilon 4 and sorry, it is T3. T3 is the same thing. It's not different in different sites. Okay. It's T3. It has heated to the same thing. It's isothermal. Let us say. This is epsilon 3 towards 2. Now the question is, sir, how do you say that epsilon can vary with the surfaces? Because epsilon depends on two things. So it is, tau is anyhow 0. We will take transmissivity as 0. So alpha plus rho is equal to 1, or epsilon plus rho is equal to 1, or epsilon is equal to rho 1 minus rho, which can go as alpha also. Correct. Now rho, which is reflectivity, can change with polishing. If you polish a surface well, the reflection is better. Same material. Correct? No. If it is rough, it has a lot of ups and downs, then absorption is better. Why does that happen? Because there is internal reflection, the absorption is second, third absorption will happen. The surface properties are same if the surface is smooth. But then what happens? There is corrugations like this. So it hit their deflection and hit again the surface. So what happens? Absorption will be more. If it is polished, then what is ups and downs is less. So internal reflection between that, because light is very small, is it not? So when you polish, the ups and downs on the surface will reduce. So you are reducing the internal reflections. So what will happen? They will reflect more. So when it reflects more, it absorbs less. When it absorbs less, it will emit less. You understand? So highly polished, high reflection. Makes sense? So what should happen here? It should highly be polished. This should be well polished, so that it will reflect. And when it reflects more, epsilon will be less. That's our purpose of radiation shield. So radiation shield are made of highly reflective. So note somewhere down. I'm going to write something here. Don't write it just below this. Leave some space, or you can write it later. Note. I'll write it here. Don't write now. Okay. Radiation shield. Radiation shields are well polished to increase reflection. To increase reflection. Very, 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 very. Okay. Generally, this space is evacuated. Okay. Now here you have this as EB1 for our 100-degree things. Yeah, it is cool. Inside it is around 80 or 90 degrees centigrade. It's fine. But when it goes more than 1000, evacuation only is not enough. You can see light coming out of it if it's 2000, 6000 degrees centigrade. It's red hot. Listen, more if infrared. Okay, but infrared is absorbed by almost every room temperature objects. Okay, when you heat more, it goes towards infrared radiation. Make sense? Okay. So now increase reflection. Okay, and reduce alpha and epsilon. Okay, that we will write it later. So here we will write this J1, then we will have this, and then this is J31, right? Then you will have EB3, then you will have you have to have this EB3, then you have J32, then you will have this, you will have J2, then you will have here, this is the J2, this is EB2, from all those things together. Fine. Five minutes more, students. I hope you're not hungry. Even if you're hungry, control your hunger. 5-10 minutes. Up till a point when you say, I cannot understand further, sir, I'm very hungry, I cannot understand at all. If you say so, then I will. Done? ಬರ್ತಾ ಕೂಡಲೇ ಕೆಳಗಡೆ ನೋಟು ಬರೀರಿ.
Will absorb more reflection.
Exactly.
That is due to too much reflection.
Exactly.
Eventually, the energy becomes zero.
Yeah, it is like how do you consider how do you do a black body laboratory black body? You have multiple internal reflections, is it not? So when you have multiple internal reflection, absorption happens. Eventually everything is absorbed. But here not all are absorbed. Some are reflected, of course. But after 2-3 reflections, what happens? With each reflections, part is absorbed. So total absorption increases, is it not? It is like what Rajiv Gandhi said. When it comes from the top till the down, you get only 1 rupee because everybody takes taxes, pay commissions. Similar. So this is Jan Dhan Yojana directly to the account. Okay, if it's polished. If it is not polished, then what happens? Everywhere commission is taken. Okay, chal. Next. Done? No, not done. Bharat ji. No, right. Important. Janadhana. Done? Okay, very good. Okay. Next. Now, if you have to have, now write it along with me, students. Q12 with one shield in between. One shield, okay, is EB1 minus EB2 divided by 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F13 plus 1 minus epsilon 3 comma 1 divided by A3 into epsilon 3 comma 1 plus 1 minus epsilon 3 comma 2 divided by A3 epsilon 3 comma 2, correct, plus you're adding all the resistances, 1 by A32 F32 plus 1 minus epsilon 2 divided by A2 epsilon 2, like this. Now if the shield, the if the surface, heated surfaces and the shields are infinite parallel plates, which is generally the case because these plates are very close by. It is shown so far. The distance between these two can be in millimeters. So when you compare distance in millimeters, and if you take even 1 meter, it can be equivalent to infinite plate, is it not? Even this thermos flask can be taken as infinitely long cylinders because between two sides it will be 2 or 3 millimeters difference. So F12 is almost one only, correct? And if you consider all these things, then yes, it is one, correct? Sure. Now, infinite parallel plates, then Q12 dot one shield can be equal to A into sigma T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1 and plus 1 by epsilon 3 comma 1 plus 1 by epsilon 3 comma 2 minus 1, correct? So if there are n shields, this one numbers I have forgotten, students, it's okay, later on we will number it, okay, in the next class we will number it. Next, now if there are n shields in between, if there are if there are n shields in between, then Q1 to 2 with n shields, with n shields with n shields is equal to A into sigma T1 power 4 minus T2 power 4 T1 minus 4 minus T2 power 4 divided by 1 by epsilon 1 1 by epsilon 1 plus 1 by epsilon 2 minus 1 plus 1 by epsilon 3 1 plus 1 by epsilon 3 comma 2 minus 1 plus 1 by so on. We'll continue like this, so on, because we don't have space there. plus 1 by epsilon n1 plus 1 by epsilon n2 minus 1. Correct? So this together I can write q1 to dot topid likana maribedi n shields is equal to a into sigma t1 power 4 minus t2 power 4 divided by n plus 1 if epsilon 1 is equal to epsilon 2 is equal to epsilon 3 1 is equal to epsilon 3 2 etc. Then n shields would be n plus 1 into 1 by epsilon plus is equal to epsilon. Okay, then 1 plus epsilon minus 1, which would be equal to 1 by n plus 1 into q1 to 2 dot with no shields. Very important, students, with no shields. This is important. So we'll stop it here. Okay, we'll continue this. I'll come back to this in the evening class because it's important. It's going in a run, so I extended it by 15 minutes. Okay. I hope you'll not mind. Okay, so it had a flight. So I'll stop recording first, then we will